Welcome, Johan, and thank you.
Thank you for this presentation. Okay, good morning, everyone. So I'll be talking about agents, neutrality, and plankton. A short trip from theoretical ecology to applied individual-based models. So in September, as Sabine mentioned, I was lucky enough to start a postdoc funded by the Biodiversity Center. So first, I'd like to thank the Biodiversity Center, if there's someone representing them here, for this opportunity. And thank you as well for this opportunity to present work past work. It's always nice to talk to a captive audience about work that I've done before. Now I say captive audience, but I believe the doors are unlocked. So if anyone wants to escape, it's still possible. So as Sabine mentioned, I did a PhD in University of Leeds, which was titled Niche Neutrality and Species Richness, exploring the link between diversity patterns and community dynamics. So what I'll be doing with this presentation is sort of introduction. The idea of this presentation was an introduction to what I've done and what I'm doing here at VSN. It's been 4 months now, so it's been delayed a little bit, but so hello everyone, nice to meet you. And the way it'll go forward, the flow of the presentation will basically be a very short introduction to the concepts of niche versus neutrality. And then I'll head on to the niche versus neutrality in the field, the work I've done in the field regarding plankton as an aquatic ecologist. And then going on to agent-based models. So niche versus neutrality and agent-based models are individual-based models, which are basically synonyms, which will then bring us to the work I'm doing here at VSL in agent-based models. So niche versus neutrality. Let's start quickly with an overview, basically. When we're talking about niche versus neutrality, we're talking about fundamental community dynamics, particularly the interspecific competition that occurs. So the competition between species. And this competition between species is something that's been shown to strongly shape the communities that we observe in the natural world. The importance of understanding all of this is, well, the thing with fundamental community dynamics is that it's fundamental. A lot of other observations and phenomena will depend on, our understanding of those will depend on our understanding of these fundamental concepts. And it's also pretty important for example, evaluating restoration projects, because as we'll see, niche versus neutrality is also deterministic versus stochastic, or not random versus random. So if we have communities that are more neutral, restoration projects tend to base their evaluation on specific communities that appear. If a specific community appeared, a goal community, then the project is seen as being successful. But if these communities are neutral or random, then we might assume that the project failed, which is not necessarily the case. And it's also pretty important for example, species distribution maps. One of the criticisms of species distribution maps is that they rely really heavily on niche dynamics. But taking into account the neutral dynamics as well can improve species distribution maps and thus forecasting as well. So with climate change, for example, what will happen to the distribution of species, it's important to take into account things such as neutral dynamics. So some descriptions quickly, so niche, I'm sure most of you already know what niches are. The n-dimensional hypervolume. We have 45 minutes of this presentation, so let's make things simple. Niches, basically, the environment is important. The different factors of the environment will determine which species persist, which species exist in a community and allow us to are then observed in nature. Neutrality is a little bit more complicated, so there's a little bit more text over here. Here's a definition I thought was pretty straightforward. So change in the composition of a community, i.e. community dynamics, is neutrally stochastic to the degree that individual demographic events, birth, death, immigration, emigration, which cause such changes occur at random with respect to species identities. So basically, what's important here is that on one hand, it happens at the individual level. So this is where individual-based models that I will talk about later, or agent-based models, will come in handy. And it's also at random. So we'll have the difference between the niche side, which is not random, and the neutral side, which is more random. To illustrate this, one example that is often used is hailstones falling from the sky. If a hailstone were to fall and kill a sprout, which is basically growing to become a tree, the species of the sprout will not be important. It could be another species. It could be any kind of species. The hailstone is going to kill one of these, and basically this death will be random. It won't depend on the species identity. So it's basically, in this case at least, death is a neutral element. So using this concept, so in 2001, Hubble introduced the unified neutral theory of biodiversity and biogeography. And this is the most basic model there is to define neutral dynamics. What basically happens is if you have a community here, well, let's say this is a plot of trees. Every shape is a different kind of tree, is a different species of tree. And you have a very big hailstone hitting one of these trees, you will get death that appears. And within that area where that occurred, you can then replace it with another species. The question is which species will appear? And that will depend on the birth from other species close by, or in the immigration from the meta-community around it. So then the species that appear will depend on these elements. As you can notice in this model, the environment itself is not important. So if we look at a local community, a species, you have either the environment is important or dispersal, so either from the meta community or from neighboring areas that is important. So you have these two elements, niche and neutrality. And for quite a while in the literature, there was debate about whether it's niche or neutrality. No, niche is important, no, neutrality is important. You had lots of different papers showing that a certain community was niche, other papers showing that communities were neutral. But currently, the consensus is that both of these occur at the same time in different communities. So on one hand, you'll have the environment, on one hand, the dispersal, and then fundamental dynamics will go from either one side of the spectrum, from being more deterministic to the other side, to being more stochastic or more random. So this is the niche versus neutrality. Having both of these in the environment, in natural communities, makes it important to be able to measure where we are along the spectrum. And the big difficulty is that measure. How do we actually measure neutrality? And there's different ways, but none of them are perfect. For example, variation partitioning, you may have heard of it, where it's basically a series of redundancy analysis tests, but without going too far into detail. Basically, what variation partitioning does is it takes your abundance information from different species throughout space and it compares it to environmental variables, to different factors such as A and B. And then you can see whether these species are more affected by A, or more affected by B, or by A and B together. And for niche versus neutrality, basically you can just replace these by the environment or space. So either the communities are more affected by their environment, or space, in which case they're spatially structured, so it's the dispersal that is more important. So the assumption is then they would be more neutral. And with both, it's the autocorrelation of the environment that basically, it's the environment, but the environment is structured by space, so it's both at the same time. Another popular metric is beta null deviation, which is basically a null model of beta diversity. Quick explanation of how this works: you basically take a community or measurements that you've had of different plots or pools or different locations, and you take this abundance information and you shake it really hard and you randomize it, and then you get a randomized beta diversity based on your abundance information. You can have different restrictions, such as the size of the different populations will stay the same, or the species richness of the different populations will stay the same. But you basically get a distribution, a randomized distribution of the different beta diversity measures that you could get if you randomize everything. And then you compare it to what you actually observe, and you can look whether what you observe is within this sort of randomized distribution or whether it's outside of it. If it's outside, then there's a good chance that the community is not randomly assembled and is thus not neutral. The further away the arrow from this distribution, the more niche the community. This is what Elwood and al. Did in 2009, though they used the C-score, which is a checkerboard metric. It's an interesting experiment where they put ferns at the top of the trees, in the canopy of a forest, ferns at the bottom, and they looked at the arthropod communities within. And if they sampled, if they did this, what I just explained, null models, and if they only took the ferns at the top in the canopy and did null models with those, and then observed and compared with the observed community, you can see that the arrow is within that random distribution. The same with the ones at the bottom of the trees. But if they mixed everything together and they made null models based on all the communities mixed together, then the observations were outside the random distribution. So basically, these arthropod communities were both structured by stochasticity or neutrality and niche or deterministic factors at the same time. So this is using, beta null deviation is using null models, and regarding null models, there are a lot of other methods that are used, such as checkerboard, extended Moricida, Schluter's index, etc. And so there's a lot of different metrics that can be used to measure this. And then the question comes, which one to use? Which one is ideal? And the answer is, of course, none. And so a lot of research have chosen preferred methods. What we decided early on was that we'd use more than one. We'd use a group of them. And to try and understand which ones are best or whether they're complementary and such. So this brings us to the first field experiment, where what we wanted to do was look at the species richness. If we inflated certain communities with species richness, how would that affect the fundamental dynamics of those communities? So we created a series of, we wanted to create a series of treated communities with higher species richness, compare them with a series of communities that are not treated, but also use a series of communities that are naturally species richer. And this was ideal in Peak District National Park, close to Leeds, in the north of England, where basically in Peak District, they're trying to re-wet the peatlands. And to re-wet the peatlands, they're installing dams every few meters along the gullies. The idea is that rain will accumulate and hold water. So what is great is it creates a lot of pools, of fresh new pools that can be used for experimentation. So we would have, for example, at the top of these gullies, pools where no water comes in except for rainwater, basically. And we could use these to create the treated pools, the non-treated pools. And then we'd have the bottom pools, which receive water from the higher up gullies. And these are naturally treated, which we'd call bottom pools. And here we can see a map of these different pools. So the gray dots are older dams that were installed quite some time ago. And the white dots are dams that were installed the winter prior to the experimentation. And so this would allow us to actually extract samples from the older pools to then distribute this sort of stock solution of higher species richness to new pools, to the top pools that are treated. And the sampling was done with plankton nets, and we had lots of different types of zooplankton. So here, for example, we have chironoids, copepods. The top left, we have cephalodella, which is interesting because they're extremely hard to identify as such because they're very plastic, very variable. So what we had to do is melt them to the trophy, which is right to the right of it. Let's see, I could try this. See, that over there is actually its jaw. So we melt it down, and it's a very small, intricate structure that helps to identify the species. And everything is very small. If you look at this square over here, that is actually a square about this size, which is 1 millimeter on 1 millimeter. So just a skim through the results. Was there an effect? Something that was quite interesting is that, well, local richness that was not different between, so here the red line is the treated pools, the black line is the non-treated pools. And if we look at the species richness through spring, summer, fall, winter, we don't see much of a difference. But if we look at, instead of the alpha diversity, so the local within the pool diversity, we look at the grouped diversity, the gamma diversity. So for all the different treatments, we see a really strong difference straight away. Already in summer, we have a very big difference for the treated pools, whereas the non-treated pools remain aren't as strongly altered. So no difference in alpha diversity, strong difference in gamma diversity. That brings, we can expect that beta diversity will then be affected. And that was the case here. If we look at beta diversity, and so here we have distances from the centroid on the vertical axis, which is a proxy for beta diversity. And we can see that in summer, we have a significant difference, and the red treated pools were significantly different from the non-treated pools. In autumn, there was no difference in beta diversity. So no difference in beta diversity. That allows us to compare the communities through what's called the primanova or Adonis. So if we, there was a significant difference in autumn with the differences in community structure, basically. So this primanova shows us for each community, it shows us the differences in community composition. And we can see that in autumn, the non-treated pools are actually significantly different from both treated and bottom, whereas treated and bottom stay the same. What's quite interesting here as well is that the bottom pools of these gullies, they tended to be very different environmentally speaking. They were deeper, they had different ions in the water, because of the fact that they had stronger flow, water flow and such. So they were quite different environmentally speaking, but the treatment was enough to bring the treated pools closer to what bottom pools look like in regards to community composition. Then what really interested us was this shift in fundamental dynamics. Did it shift the fundamental dynamics? So if we just quickly look at variation partitioning, we ignore spring because the amount of sampling was insufficient to give significant results. But if we pooled everything together, summer, autumn, winter, they were significant results. And we can see that in the non-treated pools, we actually, so the black squares, they represent the niche structure. We can see that there's actually almost half the niche structure as in the treated pools. So we could already just stay with variation partitioning. It is more niche structured with a treatment, but we really wanted to look at multiple metrics at the same time because variation partitioning isn't perfect. So we looked at beta null deviation. And before we get into all these the graphics, here we can see, so the axis is the beta null deviation. So that's how far from that random distribution I mentioned before. The higher the bar, the more niche. But then we also have lots of other metrics to look at. And it becomes complicated how to compare all these things. So what we wanted to do was sort of open the black box, try to understand how the community actually affects these metrics, looking at all the different species within the different seasons, within the different treatments. So again, a lot of information, but to simplify it, what we did was remove a species, make a measure, remove another species, make a measure again. So it's a jackknife procedure to understand how every species affects the measure itself. And then for every one of these combinations, we could then store the information as color. The redder, the more niche, the bluer, the more neutral. And we could create these sort of species heat maps. And we quickly see something that doesn't work very well, is that, for example, in summer, for the beta null deviation, we have examples where just one or two species are entirely affecting the metric. So we don't have a measure of the community, we have a measure of those two species only. And we did that with the other metrics that we were interested in, such as extended Moricida index, checkerboard, Schluter's variance, lots of things. And here, very quickly, we see the same problems. Interestingly, one, it's in winter, where there's just a few species that represent the community, and one is in spring, where there's just a few species. However, checkerboard metric is quite efficient. It shows the whole community. Interestingly, if we focus on the checkerboard metric, we can see in autumn, there is a big difference. The red, so the treated pools are much more niche structured than the black non-treated pools. And that is reflected in this sort of series of red squares, which show that the most common species, so one thing I forgot to mention, this is ordered, the species are ordered from the most common on the left to the least common on the right. So the most common species here are basically increasing the niche structure of the community. And we can see it reflected in the densities. Here we have the total density of the communities. And in autumn, always in autumn, we have that peak in density. Treated pools have had higher density in autumn. And that is also represented in the rank abundance distribution here. So the rank abundance, the highest abundant is first, then second, the second abundant, most abundant, etc. And we can see that the treated pools, the most abundant species are actually less dominated. Here we can see the non-treated pools, they're mostly dominated by the most abundant species, which is rank 1. And the slope is a bit, falls off slightly less for the species, the treated pools, so the more species-rich pools. So that brings us to the other field work that I did, where I'll skim over it a bit faster. Where here, instead of using pools, we wanted to control it a bit better. So we used large buckets to create communities that we seeded with samples from around Leeds. And we artificially created communities where the 5 most common species, we tried to get them to a similar level of abundance. And to do that, we basically had 10 large buckets with these seeded communities, and we took just 5 of them to create the low species-rich communities, and then we took all the buckets to create the higher species-rich communities. So then we have what is shown here, where the low species community and the higher species communities, we can see the higher species communities, there's a longer tail of rare species. And here, very briefly, if we look at some results, we'll just quickly focus on the 316th day, which is summer in this case, not autumn, but summer. We can see at the top, we have the evenness, so that's how even the abundance distribution is. We can see a significant difference with the evenness, which is seen here. And we have the same thing where the red, so species richer community, has a less dominance, is less dominated by the rank 1. And here, the blue ones, we can see that they are more dominated. And I wrote the name of the species here because it was the same species in every single replicate. So there was one species that was really dominating everything. Whereas this did not occur in the higher species-rich samples. So this sort of the longer tail of rare species really helped to reduce the dominance. And we see something else that reflects what we saw before, is that if we look at the checkerboard metric here, we again see much higher niche structure relative to the non-treated pool. And that is reflected in the species heat map, where we have the series of red squares that show that it's really the most abundant species that are more niche structured thanks to this higher species richness. Interestingly here, if we look at the total density, there was no difference actually, whereas in the prior experiment there was a difference. That difference, that the increased species richness sort of reminds us of what is called overyielding, where increased species richness can increase productivity, but that's not always the case. What's interesting here is that even if it's not the case, we can still detect the changes in fundamental dynamics that we saw before. So now quickly to the more agent-based model aspect. We also wanted to do work using these individual-based models. So what is great with using individual-based models is that you can do a lot of perfect replicates. And yeah, everything is a lot easier. Then the question is whether it actually represents reality better or not. To quickly explain how this individual-based model worked, as you remember with the grid, death occurs randomly among these communities. And so, for example, if one death were to occur here, so this is not a grid, it's a system of patches. Because we wanted to look at how the environmental stochasticity worked, we worked with patches instead of grids. So within every circle, you actually have a local community. You don't have one species, you actually have a large group of species within every circle. And within that circle, let's say a death occurred. The question is then, how do we replace that death with a species? And that is through this equation, which I will not go through too much, but it's always nice to show large, complicated equations. But basically, we have 3 components. We can see from the equation, there's 3 components, lambda, n, w. Basically, those 3 components are affinity to the environment, so niche, basically, and the other components are the number of individuals of that species and how far they are. So it's very logical, actually. The more individuals of a species you have that are close by, the more chances you have that species appearing. And if they have higher affinity to the environment there, then all the better. What is great, as I mentioned, with these is you can create lots and lots of replicates. And by doing lots and lots of replicates, you can then, everything is exactly the same, but if the species still vary within, what you're looking at is then how the randomness is occurring, how often randomness is important. If the environment stays perfectly the same but species change, then it's demographic stochasticity occurring. So we can basically measure neutrality directly. Here we called it SVAR. It's basically species variation among replicates. And so that's one of the reasons we did these individual-based models. We were able to measure that. And what we also did was include environmental stochasticity, which was rarely included in such experiments with individual-based models. So environmental stochasticity, what you have is the amplitude of the environment, how strongly it changes. You have the heterogeneity of the environment, how patchy those changes are. They can be less patchy or more patchy. And you have the frequency, whether they change slowly or whether they change very fast. That creates lots of different components. You have the neutral model, you have the magnitude of environmental change, of the amplitude, etc. Lots of different ways of measuring beta null deviation. We find it again. Again, 45 minutes is long. Let's go to something simpler, which sort of illustrates it. We have correlation plots for basically static and dynamic environments. So basically in the dynamic environment, the environment was changing. In the static ones, the environment was fixed and wasn't changing. And what we see that was quite interesting is here, if we focus, yeah, that works. We can see a big difference between three ways of measuring a niche neutrality and SVAR. So SVAR is basically saying that it's anti-correlated to everything else. And another way of saying it is, as we change the environment, or as we change different factors of the environment, SVAR was being more neutral, whereas all the other measures showed more niche structure. So at the same time, they were going different ways, which is surprising. One of the reasons, or the main reason this can be explained, is the concept of self-organized similarity, which is linked to niche neutrality. And I'll explain it briefly here, a bit more theory. So if we plot the community's abundance along their niche axis, so for example, from wetter environments to hotter, drier environments, or hotter environments to colder environments, we can see what can be observed quite often is clustering. So you have similar species that cluster with sort of valleys where less species occur. Well, less abundances occur in these niche areas. And what this means is that within the clusters, you have neutral dynamics that occur. But if you're looking between the clusters, you actually have niche dynamics that occur. This sort of reminds us of that tree with the ferns at the canopy at the bottom. If you're looking just at the canopy, so just in one area here, then you're going to have neutral dynamics. But if you're looking at the whole tree, so all of this, then you're going to start seeing niche dynamics, so more deterministic processes. That is also called emergent neutrality. It was called, Holtz term, coined the term in a review. And if we look at some of the results of the work, again, quickly just focusing on one aspect, here are the same sort of distributions from our model, one example of it, and we can see the clear clustering that happened. So that really explains why we have this sort of different results. So we can have higher neutrality and higher niche structure at the same time. What's interesting, though, is that if we look at the dynamic environments, we actually don't have that anymore. By looking at things in a actually stochastic environment, that this sort of difference disappears. And that sort of brought into question certain things about the importance of scale on niche and neutrality, because Jonathan Chase in a review mentioned how scale, so looking at the broader picture, you get niche structure, local picture, you get neutral structure. So scale is basically explaining what is niche, what is neutral. And that answers the question of niche and neutrality. And here we see that it's actually not necessarily the case. So it puts things back into question. So that was a very quick run through some of the work I did. And now I'll focus a bit more on the agent-based modeling that I'm doing currently at the VSL. So the project is called Developing a Visitor Flow Tool for Local Recreation, where I'm working under Matthias Buchecker and Sabine Fink. And so going from this individual-based models in ecology to these individual-based models in this project isn't that different. Even if on one side it's ecology and on the other side we're looking at social behaviors of humans, basically we're looking at nodes with edges, and in both cases we're looking at fitness. In one case it's reproduction success, in the other case it's walking, jogging, biking. And the idea here is to create a tool, a very intuitive tool that can help planners to get an idea of the situation for both sensitive species and how recreation areas are used. So by putting these two together, it's possible to really plan a recreational use while taking care of sensitive species. So the basic idea is that using map information from Swiss Topo, we can get, for example, residential areas and have agents or individuals start at specific areas. So for example, one agent would start at the residential area, which could be here. And the idea is that they then go to an area of interest. And that area of interest is where they actually recreate. And to get to that area of interest, they take the shortest route. And once within that area of interest, they recreate. And then they head back home. And we can do that for all the residents of an area. And these residents might have different preferences of different areas of interest. So they might go to different areas of interest depending on the distance, depending on how beautiful these areas of interest are, etc. And so using this map information, we can create a network. And then within this network, we can send these agents. So here's one agent. And first, they head to the area of interest, following the shortest route. And then once they are in the area of interest, they need to decide where they go. And that can be based, for example, on the nicest route, the most attractive routes, and different factors as well. And that part will be the most complex part, using social science and questionnaires that have been already developed to understand what kind of decisions users or recreators actually take. So for example, here, where do they go, left or right? Then they might go right because it's greener, it's more attractive. And then we can apply that to lots of different agents, as mentioned, all the large selection of residents in the neighboring area. And these agents can have different characteristics. It can be a single person, a family, an elderly person, or people doing exercise, biking, jogging. And that means they take different decisions based on different factors. And the idea is to get a map that shows the path usage. So then we can understand where people tend to visit more often. And here is a quick look at the tool itself. So for now, it's mostly trying to get it to work exactly the way we want it to work. So it'll look nicer later on. So we can, for example, it has to be intuitive. So it's a stepwise process. First step, we can put in coordinates or a shapefile, for example. So if we put in coordinates here of Berensdorf, for example, we then get images that represent based on Switzerland and also zoomed in if we put in the right coordinates, if it is exactly what we want. So this is around Berensdorf. Then the tool will basically go get Swiss topo information, cut the paths, make sure that there's a node, so that's the little circles, at every cross section, because the agents can take a decision at every cross section. So that, and then we can explore it, make sure everything is the way we want. Then we get to step 3, where we can actually choose the species that interest us. So the sensitive, and we can create the sensitivity matrix that will determine where the areas are more sensitive, either by selecting species directly here, or through groups such as their classification or characteristics. Are they aquatic? Are the planners making something that might affect water, in which case they'll be more interested in all the aquatic species, for example, etc. And here the list of species actually also gives, so the list is from the most present, to the least present, from top to bottom, based on the species distribution maps we have. And then all the information such as priority in Switzerland, vulnerability, etc., can be presented along it. And then finally, we have to select the area of interest. So this is not the areas of interest themselves, but we're using a sort of attractivity model that defines which places are more or less attractive in Switzerland. And the thing is, if you're in a place that is very green everywhere, you'll still want specific areas of interest to go to. But if you're in an urban area and you have a small park, then the area of interest might be something as small as a small park that isn't even really that attractive. So you need to sort of determine manually how the areas of interest will look by just sliding a single slider. So once you think, okay, these represent the areas of interest of my region, you then get these polygons representing the areas of interest. You can still manually modify things, erasing by clicking on them, for example, erasing that one, or clicking on an empty space to create a new area of interest if you so wish. And then it's the fun part of just launching launching agent-based model that represents either a day of the week, a whole weekend, a day of the weekend, as those different days might have different agents walking through them, more elderly people during the week, for example, or more people exercising in the end of the day, etc. And then it launches the model. So this isn't shown, this is just a debugging process where we can just see one agent, how they're moving, shortest route to an area which is the outlined area of interest. They then stay in that area, navigating, recreating, and then they head back home. So the gray dots are simply where they were before. They head back home. And once all the agents returned home, we get sort of a usage map, which shows how the areas are mapped. So it's still very much work in progress. Here you can see little purple dots, where basically agents are sort of turning around on their own, which needs to be ironed out. So still a lot of work to do, but yeah, that's a quick skim through all that. There, thank you. If you have any questions, or happy to answer them.
So thank you very much, Johan, for the nice overview. Quite a different talk from like experiments to models to now an even more sophisticated approach. So are there any questions? Yeah.
Thanks for the talk. I was wondering to make the bridge with the first part, ecological part, do you plan to add like any stochastic process in the agent-based model? So do they like behave sometimes stochastically, so not taking always the shortest path, but just turning left because they won't, I don't know why.
That's a very good question. It's actually, it was explained in one of the slides that I removed to try and reduce everything. Um, so it will be taken into account because the different factors, such as whether a path is greener and another one is less, or whether there's a stronger slope in one area or another, etc. All these factors will actually contribute to probabilities. So agents will have a probability of choosing a specific path, but they won't necessarily choose it. So that's where the randomness comes in, because humans are complex. Sometimes they have a bad day, sometimes they feel adventurous. So sometimes they might choose the one that has less probability of occurring. So then we'd have to launch multiple replicates to really take into account that stochasticity.
Okay. And do you have interactions among agents?
So that is possible. So the main interaction that we are thinking of using is crowding. So if an agent gets to an area and there's a lot of other agents already in one area, they might find it less attractive and go somewhere else. So that is an idea.
Thank you for the talk. It was very interesting. I have a question about the neutrality concept and the fact and how you defined it as being something stochastic at individual level. In population genetics, we often refer to demographic processes as natural processes occurring in nature. So it's not necessarily stochastic in a way that immigration can have, for example, in the context of climate oscillations, different routes. And then in the end, natural processes are structuring this community independent of the environmental conditions. Is it something you explored in your analysis, or so distinguishing demographic processes from stochastic effect? So it's probably a question of scale.
We assume that the stochastic effects that we observed were based on demographic processes because we were comparing similar environments. So, for example, they wouldn't come from environmental stochasticity or as such because we're comparing similar environments or similar effects. And so we assume that any kind of stochasticity that we observe, for example, in the modeling as well, any throughout the replicates, any kind of variation that we observed, so demographic stochasticity would be assumed to be entirely, well, it would be demographic stochasticity and not based on other stochastic effects. But I'm not sure if I actually.
So, for example, if we have two different recolonization routes, after glacial oscillations, after the last glacial maximum, we could imagine to have contact zones where communities are recolonizing the land from different origins, and then we would have demographic processes going on without strong environmental, effect.
Okay, so kind of like priority effects, or
yeah.
So yeah, no, that we sort of assumed that yeah, we didn't take into account priority effects. So no, to answer the question, that is one of the reasons. Yeah. No, we didn't take into account that in the study.
I don't even know even if it's relevant actually, but just an idea coming from this population genetics debate we have.
Okay. Okay, thanks.
So there was one question online, right? Or two now, okay.
Okay, so these questions are both from Catherine Graham. She asks, do the agent models vary across year, i.e. mushroom hunting periods, or bird watching, i.e. spring when species come through, might influence their behavior?
Sorry, can you ask again?
Yes. Do the agent models vary across the year? So I think like during the different seasons of different activities that people might be doing.
So currently, it is not the priority, but it is something that can be done. We are thinking of perhaps including seasons, or at least implementing a way of including seasons later on. But that would not be the priority for now. But it is something that can be quite important, definitely.
Thanks. And then she also asks, I really liked the moving window, as this then brings in a landscape perspective, if I understand correctly. How do you choose the moving window, and how do you have, and do you have predictions associated with the size of the moving window?
So the moving window, sorry, I'm not quite sure I understand what she's referring to.
I will wait for her to respond.
So the moving window, which so was
Is
that
this what you mean, Catherine? Oh, he said something about the different grid sizes of the site. Yes, I think this is what she was referring to.
the different grid sizes? So was it with the agent-based model, this part of the talk?
Yes.
So the different project. And so the moving window, so here, so it's not really a moving window. It's you can either implement coordinates that they can be larger, smaller, and basically it creates a square around the area that is of interest. You can also import a shapefile, for example. And the idea will be that later we can also just drag and drop either KML or .shp shapefiles to really create the region that is of interest. So it's not a sliding window.
Yeah, and she added the green means different things depending on the landscape for the greening.
Depending on the landscape.
So green in a city or green in a place with lots of green means
yes.
different. Yeah.
Yes. So here, yes. So yeah. And what was the question based on this? Sorry.
Let me go back up. So yeah, how do you choose this window, and do you have predictions associated with the size of the moving window?
So the idea here is to actually allow the planners to choose the windows. It could be possible to determine, for example, a specific size that areas of interest tend to be for people, if we can get that information from questionnaires or such. But the idea is that because things are so relative, here it would allow people to really determine what are the areas of interest, and then by overlaying it with a map, we might be able to see whether it actually fits with, for example, forest areas and or parks, and whether that's the right size or not. But relying entirely on attractivity of different things makes it complicated, because different areas, a whole city can be attractive, and then you just have one big block, and that's not very useful.
Thanks.
So as time is advancing and there's no additional urgent question online, so I think the others can also ask